All right, just getting started. This is today's Zoom session for June 3rd, our last one. The quiz is going to be posted at noon, made available this Friday, due Saturday. It's on this topic. So there's only one section of the reading. I believe it's section 17.3, I want to say, but it's in the reading and practice problems for this unit, chapter 17. So if you recall, the functional groups called esters and amides, they look like this. So an ester has a carbonyl group, but it's also got an oxygen on one side. And the implication is that there's carbons on both sides of the ester to make it, in fact, an ester. Amides are very similar. They have the carbonyl, but instead of an oxygen here, they have the NH, sometimes NH2. This also implies that there's carbons on both sides. So this should be review of esters and amide functional groups. These are really important functional groups in nature. Really, all of this goes back to nature. Aspirin has an ester functional group, right? It also has a carboxylic acid functional group here. Penicillin has two amide groups in it. There, and there's amide groups. There's another carboxylic acid group, sulfide, actually. And then the R group can vary because there's a lot of different kinds of penicillins. So clearly it's important to be able to synthesize compounds that contain esters and amides. They're among some of the most important drugs, as you see, and other compounds in nature. And so I've decided to focus on just that aspect of it for this final unit. And the synthesis of esters to begin with. So we can make esters from a carboxylic acid, again, functional groups, right? And an alcohol. And I basically color-coded it. So what ends up in the final product is all of this linked to this. The oxygen of the ester that results is donated actually by the alcohol. It's not this oxygen of the carboxylic acid, that leaves. So it's one thing to just recognize a reaction, it's another thing to understand it, which the idea behind that is that understanding it helps us remember it better. Understanding it will also help us understand the next reaction with amides to synthesize amides. And you will see that if you understand one, you'll understand the other very easily, I think. So adding that little breadth and depth, the mechanism of esterification is first initiated by the alcohol oxygen lone pair, one of them, forming a bond. And then that displaces electrons up onto this oxygen, which then, having extra electrons, becomes a negative oxygen. So this set of arrows results in this new bond right here, and the breaking of one of those double bonds to oxygen, leaving a negative charge there. The OH group is still hanging on here. There's just a brief intermediate step of deprotonation, and we've seen a lot of those. just hydrogens popping on or off. In this case, it's this hydrogen gets removed probably by water. That's an easy enough reaction. And that brings us to here, which is primed for reforming the carbonyl group and displacing off the OH as a leaving group. So this leaves, leaving group, leaves. And this reforms the carbonyl group here, reforming that bond, and that doesn't look very good. And there's our ester product, see the ester group. So it's easy to imagine that if you vary any of these groups hanging off either side, you can create a whole bunch of different esters, basically an infinite variety. Literally an infinite variety, I should say. The synthesis of amides is pretty much the same deal. So we have the same exact setup here. The only difference is the amine group rather than an alcohol. And the contribution of the carbonyl group and the rest remains the same. And here we contribute an NH and then the rest of it. So that's where these come from. There's the new bond that got formed. Notice that in both esterification type reactions, there's loss of water. Loss of H2O, common to both. So that's another way of recognizing another aspect of this kind of reaction. The mechanism now is essentially the same. So again, you can memorize the reactions as they appear on paper, or you can learn the mechanism and recognize many more of the same kind of reactions, not be left scratching your head like, is this the same kind of reaction or not? So the arrow pushing is exactly the same, the bond forming, bond breaking. There's the new bond that formed, the negative charge on oxygen, the deprotonation, all the same as what we saw above. Loss of hydrogen, one of these hydrogens. Notice the charges change, but then we have the exact same electrons come down to reform the carbonyl group, kick off the OH as a leaving group, the exact same leaving group as what we saw above, and there we have our amide product. So just taking a look, okay, we looked at the functional groups, the kinds of compounds that contain amides and esters, the basic synthesis of esters from a carboxylic acid and an alcohol, that mechanism, the basic synthesis of amides from a carboxylic acid and an amine, essentially just substituting the alcohol oxygen for an amine nitrogen, creating amides, and we've proven now that that's really the same exact mechanism. So we have both the breadth and the depth of those two reactions. So looking at a couple just other examples of the same stuff, noticing that we can vary the things that are attached on both sides, but that the common elements are the same, literally the common elements are the same. So formation of the ester bond essentially will get us to, and then, you know, the additional steps in between that we saw above will yield this ester with loss of water, right? Loss of water right It's an easy way to see it. Another example of an amide doing the same kind of thing. Oh, keep my colors consistent. So the lone pairs on nitrogen, forming a bond there, displacing electrons there. Those electrons come back down, kick off the OH group, gives us the associated amide. And there we have that. So pretty much becomes trivial when you can see the key components of what's being linked to form the ester or the amide there and there. And that all these other groups are just sort of spectator groups, aren't they? They're just watching the action from the sidelines. It's not too hard to imagine, since you're starting with a carboxylic acid in both cases, that you can make an ester in one instance and an amide in another instance. Here you're asked to provide, for example, what reactants you need to go along with the carboxylic acid to get to the ester or the amide. So all you have to do is refer above and mix and match or plug and play or however you want to say it. So clearly this component is donated in both cases by the carboxylic acid, right there. And so in the top case, when you're making an ester, we need an alcohol that looks like this. So that's really pretty easy to do. If I can draw better. Okay. That's pretty much the alcohol that you can use to make this ester. And again, here, that's going to form a bond there initially. And then on the bottom side, you've got this piece of it that is needed in the other reaction. So all you got to do is remember that amines start out that way if they're neutral. And there's our amine part, amine, alcohol, carboxylic acid. And clearly, once again, same key bond forming step initially with the nitrogen forming a bond there, which is the amide bond there. Okay. So other than penicillin and aspirin, there's, like I said, there's really important compounds in nature that contain, in this case, amide bonds. And probably, well, it's hard to rank the importance. Amino acids are among the most important compounds that have amide bonds. If anybody is going on to Chem 113 biochemistry, you're going to see a lot of amino acids. And probably some of the same chemistry. So the general structure of an amino acid is this: amino, terminus, carboxylic acid, terminus. So it's an amino acid. In between is this carbon here connected to an R group, which can vary, right? We know R groups are basically like wildcards, can vary. And I'll point one other thing out just for interest. That is a chiral center right there, almost in most cases of amino acids, I'll say. So you can link one amino acid. If we bring another amino acid in here where the R group can be the same or different. Oops. And clearly we can see that we have the same setup as above with a carboxylic acid group and an amine group and the potential loss of water to link up in an amide bond. So showing this reaction with a specific example, valine is an amino acid, tryptophan is an amino acid. Notice these are the R groups. There's an R group there, R group there. So bond forming kicks those electrons up. What I can do here, since it's a lot to draw, I can do this. M, H plus. One more look at the overall mechanism. C, O, H, O minus, connected to. That's really right, the center of the action, all right in here. And then we have the deprotonation, loss of one of these protons. And H, so nitrogen is neutral once again. C, OH, which is going to be our leaving group, O minus, connected, and, oops, move over a little bit. And then this comes down, forms the carbonyl, kicks that off. Now I'll draw the whole thing just for completeness. So we have the valine. I always remember valine because it's got this V shape, kind of upside down V. And H. Now we have the new bond to the carbonyl. There's our new bond. C, H, H2. And I'll point out some interesting features here. There. So we would call this valine tryptophan. Or they have these abbreviations, VAL, TRP. And another thing to really notice is that you have still a carboxylic acid on one end, an amino group on the other end. And clearly you can continue to add amino acids to either side. So just continue to add one amino acid after another can continue to add to both ends, at least until you run out of reactants. This would be how you make a really long amino acid chain of amino acids all linked together, which has the name of a it's called peptide chain. When peptides get to be even larger, like incredibly large, they essentially form these gigantic chains that begin to loop around each other, sometimes cross-linking, and we call them proteins. So you're going to see a lot of that in biochemistry. So to peptides, and eventually to proteins. This is why organic chemistry relates directly to and precedes biochemistry. because all the protein in our body, all the muscle in our body is made of protein, is a quadrillion or whatever godzillion number of amide bonds that have formed. Okay. With the remaining time, and we'll probably still finish early, I think, I was going to just show an example of some chemistry from previously all quarter. Remember, we have a comprehensive final. Probably the best way to study for that would be to go over all the old quizzes and expect to see similar questions to those. So if we look back at, we saw this compound earlier, menthol, for example. This is just an example of sort of putting together all the knowledge that we've acquired all quarter. You can look at a molecule like this. You should be able to draw all the implied atoms. So you should be able to redraw it like this, for example. And know where all the implied atoms are. And I must say that this is still something I believe that people struggle with because they're missing aspects or parts of questions that I feel is because they lost atoms or failed to recognize where atoms were or weren't. So it's not a bad idea to practice this again if need be. Ooh, I almost forgot one there, right? So, did I get them all? Yes. This would have the molecular formula 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, C10, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, O. Hopefully got that right. You can check me on that. I was going fast. The name of the functional group should be easily accomplished as alcohol. And it's a secondary alcohol, right? Because the carbon to which the alcohol is attached is connected to two other carbons, there and there. That's how we name, remember, primary, secondary, and tertiary alcohols. So there's menthol, there's the functional group in it. We should be able to predict reaction of menthol. Back in the alcohol section, we saw that alcohols can be protonated easily in aqueous acid. So recall that whether you have sulfuric acid or hydrochloric acid or whatever, if it's in water, essentially you're forming a hydronium ion like this as the reactive species. But however you want, alcohols can pick up a hydrogen from acid. Showing the details here, that sets up this OH2, now a plus charge. That relates to the number of electrons around oxygen, and everything else is still the same. And now this is set up as a great leaving group. I'm going into the details of this, but we learned it in the net reaction as well, which I'll show after this. So remember that you can eliminate now. Water can come along and create a double bond in this way. Just reviewing the mechanism, resulting in a double bond there. This was way back when we were doing, how do alkenes react? How do alkenes get formed? So we've got this material now. So it may be more familiar looking if you consider that you're basically just going from here, a little bit to draw, H3O plus, however you learned it best, we studied this reaction and pointed out the key changes occurring here. So this is, what you would call the net reaction, and above is the mechanism, which is intended to help aid in remembering and understanding. Now that we have this alkene, we can, in fact, react it further. In one of the alkene reactions that we learned. So remember how this goes. The double bond can bond to the hydrogen, kick off the bromine. It's another stepwise thing. And initially you get a plus charge on one of the carbons, and the other carbon having picked up a hydrogen now has two. Drawing in the implied hydrogens helps. Hopefully all this looks familiar from way back. And the bromine is still floating around as a minus, and that in a second step comes in and bonds directly to the plus charged carbon, giving us HBr, H, and essentially we've added HBr across the double bond. So from over here to over here would be the net reaction. I just showed the mechanism because it's what I do. But another thing to point out, or a couple more things to point out, except I need more space at the bottom. Okay. And another thing to point out here is that let's look at this one more time. If I was to draw this sort of more on edge view, and I guess you'd have that pointing up there and that sort of down there like that, I guess. Do this. This, if I bold these a little bit, it even helps more. These are trigonal planar carbons. Trigonal planar. So, brief reminder of the geometry stuff that we did. Tetrahedral, trigonal planar, linear geometries. Excuse me. And then, so at the point here at the very beginning where it reacts with the HBr, it's really this pair of electrons here reacting. Remember, there's a carbon there, carbon there. This is flat. So this arrow I'm going to draw here, forming a bond to the hydrogen. Realize that that can happen on the top face, as I have it here, or can occur on the bottom face, because this is flat, essentially. Trigonal planar is flat. Can happen below, for want of a better word. So if that's the case, then you've got, if I can draw this one more time, this is really the last thing I have today. Well, almost. No double bond. So now this carbon, for example, we've added a hydrogen to it. Now this is tetrahedral. And this is going to look the same whether it happens above or below. We're still going to get to this point. However, in the next part, oops, with the bromine, this can now come in from either face of the molecule. And I'll show those options like this. Top or bottom. So that is going to lead to the bromine being either up or down with respect to the other groups in the molecule. So to draw that, I'm going to go back. Oops, I'm going to go all the way. I'm going to go back to the original view here because we have all we need to know now. This hasn't changed. This hasn't changed. There's two hydrogens here now, and that's tetrahedral. But in one version, you have the hydrogen up and the bromine down. And in another version, which is equally likely, you have the hydrogen down and the bromine up. And at this point, you can see where my thoughts are heading, I think, which is to review R and S, because that's what we're looking at here. Incidentally, so this carbon and this carbon are also chiral, but they don't change throughout the course of the reaction. So just examining the chirality of the part that does change is our focus. Chiral center, chiral center. I'll do the one on the right first because it's set up easier, right, with hydrogen pointing away from me, from us. Priority groups, bromine 1, hydrogen 4, that's easy. And then we have CH2 versus CH bonded to carbon-carbon. So from the point of view of this carbon and this carbon, it's tied. As we go out further from this carbon, we have H, H, and carbon connected directly. From this carbon, we have an implied hydrogen and carbon, carbon. So this one wins in the battle for number 2 and 3. This is 2, and this is 3, getting tiny. 1 to 2 to 3 with 4 pointing away from us is clockwise R, which means this one by definition is S. And so, but you can always double check because you already have the priorities assigned. 1, 2, 3 clockwise. However, with 4 pointing toward us, it's not R, it's S. I guess I could do this. So even just this one molecule, asking a few simple questions about it, you know, show all the implied atoms so we know what we're dealing with. Identify the functional group. Know how that functional group reacts in acid, resulting in an alkene. Knowing that alkenes can be hydrobrominated or whatever, H and Br added to it. understanding that the geometry of alkenes and what results in the first step here are still flat and have a top and bottom face to which things can add. And when you have an equal likelihood, then you get a situation where you have isomers of some sort, in this case, stereoisomers. It's kind of nice to just see all of the chemistry, not all, but much of the chemistry of the quarter applied to one situation, for example. I mean, we did a lot more other chemistry too, but just as an example. So that's all I have today. Actually, this final Zoom session, it's finishing a little bit early, unless there's any questions. I have my fingers crossed that it is still recording. And so when I press stop, it should tell me it's not recording anymore. If something goes wrong, like I said in the announcement, I'll re-record voice over this, I suppose. But I'm optimistic that it worked. All right, so I'll sign off. Thank you for coming and thank you for listening.
Thank you.